Okay, hi everyone. So let's solve one question on a centrifugal flow compressor, and this is not a numerical. This is kind of theory, and they are checking your theory understanding. Okay, and students are struggling to solve this question in our test series. So I thought to provide a solution. So let's see this question. This is kind of interesting and tricky as well. So consider a centrifugal compressor with a backward curved impeller blade. Okay, operating under steady condition. This is fine, right? Till this point. The whirl component of absolute velocity at the inlet is zero. Now this is important statement to understand. Okay, that, and they are saying that this component is zero. You consider this component as a zero. What is the meaning of this? If you have understood the velocity triangle properly, you will come to know that if they have provided this statement, that means you are not having the inlet guide vane, so we need not to worry about the inlet guide vane. And also please understand, keep this in mind, that we are talking about the backward curved blade. Okay, so there is an important reason to give this statement as well, otherwise it is difficult to solve this question. Now they are saying consider u2 is a blade velocity. We know already, right? This u2, alpha 2 and beta 2, these are the usual notation as we have seen in the velocity triangle of CFC, right? So u2 is the blade velocity at the impeller outlet. Okay, this is important, impeller outlet, so that you will come to know where we are talking about the location, right? Then alpha 2 is what? Your air angle, or you say absolute flow angle at the impeller outlet. Alpha 2 they have given, right? So we are talking about the station number 2, which is impeller outlet. Then alpha beta 2 is the relative flow angle at the impeller outlet. It is also, we name it as a blade angle at the impeller outlet. Now they are saying the specific work done by the impeller on the fluid can be expressed as which of the following. Now they have given you the 4 option. What I'll suggest you, that please pause this lecture and try out by yourself. Students are trying to solve this question, but they are not able to solve in the test series. So this is a question of a full mock, first full mock exam, okay, in our test series. So I thought to provide a solution, because most of the students are not able to solve this question. Either they have not focused on the velocity triangle, or they have not stressed on at the time of full mock exam, because might be this is on a trickier side though, so they thought that this will take more time and they have probably skipped this question. So this might be the two reason. So let me provide a solution and we'll see. Okay, so let's start the solution part. Okay, so before starting this question, what do you think, from where we should start this? So the first thing, if you see, if you don't have any clue to start the question, first see the options. So in this we got a one clue, that the options are talking about in terms of the blade angle and the alpha 2, beta 2, everything, right? So these four terms are present in all the four options. These three terms are present in all four options, right? So we'll start from the specific work expression. Now specific work in a centrifugal flow compressor we have seen in terms of either we have seen in terms of this one, and we have seen in terms of this one, and many more, a few expression as well are present, they are also present, right? So but if you see these equations, these expressions are not helpful for this question, right? As well as this equation is not helpful for our for this arrive at the solution, right? Why? Because these equations are not representing these terms, right? Alpha 2, beta 2, they are not we are not having this. So what we can do, first thing, we can start from the Euler turbomachinery equation. So if you recall, I have given you this equation, Euler turbomachinery equation I have given, and this equation is derived from, let me write this first. This equation, if you recall, u2 ct2 minus u1 ct1, and this equation I already given, and this equation was derived from, we have not seen the derivation, but you should know from where this equation is derived. And this equation we got from conservation of angular momentum. Okay, so please, you should have this, because many time in the interview you already know this equation, but they will ask from where this equation is derived, from where you have got this equation. So you should know that this is derived from the conservation of angular momentum. So at the time of interview it might help, it might be helpful. Okay, so let's proceed on this. Now the first thing is, they have provided you a one condition, that at the inlet you have a zero absolute velocity. That means in our notation it is ct1 is 0, right? That means you not have the inlet guide vane. So ct1 is 0. Now this term is gone, right? Now you are end up with this expression. why I have now you might be appreciating that why I have arrived at this expression, because my options are in terms of this. If you see, u2 are already present in this expression. In every option u2 is present. Now you need to modify this expression. You need to modify this expression in terms of the alpha, and beta, so that you'll arrive at this kind of expression. Okay, so now what you can do, now if you see, these expressions are in terms of the beta 2 and alpha 2, right? Similarly here, alpha beta 2 alpha 2 beta alpha 2 beta 2. So now you need to modify this expression in terms of alpha 2 and beta 2. Rest is similar. u2 is already present here, right? So we need not to touch the u2. We will automatically get whether it will be u2 square or simply u2, we'll get this. Okay, so now we need to modify this expression in terms of the alpha 2 and beta 2. So what you can do in this is, we need to start from the velocity triangle. The reason of starting from the velocity triangle at the impeller outlet is that you have an expression in terms of alpha 2 and beta 2. That is the reason we need to go to the at the exit of impeller, that is station number 2, alpha 2 and beta 2, right? Let's start with the velocity triangle. So now the importance of giving this statement, backward curved blade. Now you will use the velocity triangle of a backward curved blade or backward curved impeller. You will not use the radial, you should not use the radial blade velocity triangle or forward blade velocity triangle. There is a reason. That is the reason they have provided this expression, so that you will go towards this one. Okay, and we know in our aircraft application, we always try to get a performance of a backward blade or a radial blade, right? Okay, anyway, so we'll draw the velocity triangle. So this is the velocity triangle of a backward curved blade, right? And this is at the station number 2, guys. Okay, station number 2, that means at the exit of impeller. Okay, outlet of impeller, and this component is a absolute velocity, and this component is the relative velocity, and this is the axial velocity of a CR. You write CR2 or you write CA21 in the same thing, as far as your understanding, that is fine. And now this component is CT2, tangential component, or you say wall component, and this one is WT2, and this whole component is a, this one is the blade velocity at the impeller outlet. You write this as a u2. Okay, and this is alpha 2 and this is beta 2, fine. And these are the perpendicular stuff, perpendicular component. Okay, now what I'll do, we need to modify this CT2 in terms of the alpha 2 and beta 2. So for that, what I'll do, I'll use the trigonometry. So in the trigonometry, we'll take a tan component, and there is a reason that you will come to know why I'm using the tan component. So that my equation, my expression will be in terms of alpha 2 and beta 2. That is the reason only we are taking the tan component. So tan alpha 2, you take tan alpha 2 can be written as height by base. So CR2 divided by CT2, right? This is height and this one is the base. Okay, now you can take, now you can also write, okay, now you can take tan beta 2. Now tan beta 2 again can be written as a height by base. Okay, so CR2, and what is base? This one is base, WT2. Okay, those who have done the velocity triangle, or those who have done the centrifugal compressor properly, okay, those who understand the velocity triangle understanding is also required. Then and then this question is, you will be able to understand, otherwise things will be here and there only. Okay, so better you understand the velocity triangle first. Now what you can write from here is CR2 can be written as WT2 tan beta 2, right? Similarly from here you can write CR2 as a CT2 tan alpha 2. Now what I'll do, this WT2, we'll write this as a U2 minus CT2. You will come to know why I'm doing this. Okay, so CR2 from here can be written as U2 minus CT2 multiply of tan beta 2. Now what do you do again? You multiply this tan beta 2 inside, and you will end up getting this as a U2 tan beta 2 minus of CT2 tan beta 2, right? Now what I'll say, you consider this as a equation 1, this one, and you take this as equation 2. Now we can equate this, right? This is these two left hand sides are same in the both the equation. So equate equation 1 and equation 2. You'll end up getting this as a CT2 tan alpha 2 is equals to U2 tan beta 2. I'm writing this one minus of CT2 tan beta 2, right? Now what I'll do this, I'll take this term into left hand side and I'll take CT2 common from here. So I'm directly writing the equation which from where I have taken CT2 common. So CT2 you take common and tan alpha 2 plus tan beta 2, and this right hand side will remain as it is, this one. Now what I'll do, I'll take from here we'll try to compute equation of CT2, and that can be written as a, okay, so we'll write the angles in a bracket beta 2 and U2 will keep it as outside. Now this is the expression for a CT2. Now I hope you understood why I have arrived at this solution, so that I'll substitute this CT2 directly in this equation. Now final equation will modify in this way. You can write this as a specific work. Okay, specific work can be written as now U2. Now this U2 and U2 become square. Okay, so U2 square will U2 square, and in the bracket it will be, okay, it will be simply tan beta 2 divided by tan alpha 2 plus tan beta 2. So we have arrived at the expression for specific work, calculation of specific work in terms of blade velocity at the impeller exit and the alpha 2 and beta 2, right? So I hope it is clear, and option A is correct, right? Option A is matching. Okay, yeah, option A is matching. So I hope you understood how to approach this question. Okay, first of all, because this is slightly new question, right? We have not solved this kind of question even in the previous year, your GATE Aerospace previous year question. You will not find this kind of question from the centrifugal flow compressor, even from the axial flow compressor. So you need to have a proper understanding of a velocity triangle, so this kind of question, if you want to solve, you have a more number of question practice, then your mind will open up for solving a different kind of question. If you know the formula, then numerical questions are easy for you, because you need to use the formulas and here and there you know substitute and end up getting a one expression, one value, right? But when it comes to the, so the here you need a derivation, small derivation, right? For that you need to have understanding of a velocity triangle. So just formula will not help you here. You need to have a proper understanding of velocity triangle and different equations. Otherwise, if you would have only learned this expression for a centrifugal flow compressor, this one for radial blade, this will not help you here, right? Okay, so anyway, I hope you understood a few things from here. If not, if you are having any doubt, you can ask me as well, and I'll also suggest you to please remember this one. So if someone asks in an interview, if you're appearing for MS or PhD interview, if they will ask from where the Euler turbomachinery equation is derived, then you should know that it is derived from the angular conservation of angular momentum. Okay, so let's meet in the next lecture, guys. Bye bye.